So, if you take a look at Mod 4 for investigation, we're going to be exploring those exponential functions a little bit more, okay? So, if you take a look at our first one here, what does b to the fifth represent? Well, it is the product of b as a factor 5 times. So let's write that. It's the product of b used 5 times. And then let's take a look at the second part there. It says evaluate 4 to the third, and what does that answer represent? Well, 4 to the third is 4 times 4 times 4. Most calculators, you can use that caret button. iMath, I believe, the same, but you would get an answer of 64. And that just means that the product of 3 factors of 4 is 64. Now, B is trying to get you to understand that anything to the half power can also be represented as a square root. So getting that in your head, getting used to the idea that a half power is equivalent to a square root is a really good thing to know. So, when you see 9 to the 1/2, if you immediately think that is the square root of 9, that's great. Now, let me show you why it ends up working that way. 9 is the same as 3 squared. The rules of power say that if we have a power on the inside of a parenthesis and the power on the outside of the parenthesis, we multiply. 2 times a half is 1, so it becomes 3 to the first. So if you see it in that light, you can see how quickly it becomes 3. 4 to the 1/2 is the square root of 4. Or since 4 is 2 squared, that's why the answer becomes a 2. And then finally, 121 to the 1/2 power is the same as the square root of 121. Since 121 is 11 squared, the answer is 11. Okay, so you can think about this as a square root. You can think of it as, just a half power. And, you can go from there. You can also think if I have a half power and another half power, I should get that base number if I multiply them together. So the square root of 9 times the square root of 9 is 9. So the square root of b times the square root of b is just b. We know that, but relating it back to a power instead of that square root symbol becomes important, okay? D is moving on to think about what a 1/3 is. A 1/3 power is the same as a cube root. Anytime you have a fractional exponent, this is going to still represent as a power. This is going to be the index in your root. Okay, so what do I mean by that? Well, the denominator goes inside that radical symbol. The numerator stays as a power. So it's really helpful to know how to go back and forth between a fractional exponent and its radical power equivalent. So what's interesting about E, I'm going to show you 2 different ways to do the problem. 4 to the 3/2. Since 4 is 2 squared, let me make that square look a little nicer there. That's 2 squared. The rules say that if you have a power on the inside and power on the outside, we're just going to multiply. 2 times 3/2 is 6/2, or 3. So 2 to the third power is 2 times 2 times 2, or 8. Now that's, I think, the quickest way to find that our answer is 8. I'm going to show you another way, okay? If we rewrite that that 1.5 is 3/2. How do I know that? Well, 1.5, if I multiply by 2 on top and bottom, anytime I see that 0.5, I think halves. And so if I double that, that's where I got the 3/2, if you're wondering. So that fraction is more helpful than a decimal. Okay, so anyway, any way you go there. What I would suggest doing here is if we rewrote that 4 to the 3/2, 4 to the 1.5, if we put the 2 inside here and the 3 inside here, watch what happens. Now, the 2 is not normally written for a square root. That index is implied. If you don't see it, it means it's a square root. If you do see it, it's some other type of root. So if you write the 2, I'm okay with that. It doesn't hurt anything. But you don't have to if our denominator is a 2. You can, you don't have to, doesn't matter. If you evaluate the fact that 4 cubed is 4 times 4 times 4, or 64, we know that the square root of 64 is 8, since 64 is 8 squared. So as you can see, there's lots of ways to get to the answer 8. Okay, you can break down the inner stuff, then evaluate the power. You can rewrite it and calculate the inner stuff, get a larger number, and then break it down into a smaller. So it's up to you. However we do it, you should get an answer of 8. Now, if you were to put this into a calculator or into iMath, yes, feel free to use the caret button, but you want to put the 3 divided by 2 in parentheses so that it knows the whole 3/2 is part of the power. If not, they'll get confused. They'll think the 3 is there, but the 2 isn't, so be careful with that, okay? Okay. Now, as far as solving equations like f, the even powers, like 2, we have to insert the plus or minus symbol, okay? So this one, it would be plus or minus the square root of 81, or plus or minus 9. But since this whole power is odd, we don't have to do that. We just can go ahead and cube root it. The answer is the cube root of 27, which is, in this case, 3, because 3 times 3 times 3 is 27. Now, I wanted to show you how to deal with fractional exponents, because you guys will make it harder, because it's just naturally, then you have to. So this little F3 and 4 are a little funky, okay? So let's talk about these. To get rid of a fractional exponent, we are going to use the reciprocal. To get rid of fractions in general, reciprocals are going to help us. Okay, so this is what you're going to do. Surround them by parentheses. The reciprocal of 3/4 is 4/3. So we have to use a 4/3 power to get rid of a 3/4 power. So this just becomes x to the 12 over 12, or x to the first. That's what we want. We need to know what x is. Okay. Now, if we use our rules of exponents, I'm going to show you 2 different ways to solve it. 8 is 2 cubed. The 3's cancel. We get 2 to the 4th. 2 to the 4th is 2 times 2 times 2 times 2, or 16. Now, that's one way to solve it. Now, I want to go backwards just slightly to here, and I'm going to show us how to get to a slightly different point. Same answer, but a different method. Rewrite that as the cubed root of 8 to the 4th. Now, the reason I like this method is because you'll notice I never pulled out a calculator. I was able to do a lot in my head. I do not know what 8 to the 4th is, because it's 64 times 64. I don't know what that is. It's a very large number, okay? So 8 to the 4th is 4096. But the cube root of 4096 is indeed 16. So I tend to go the route, make it smaller and break it down, because I can do it without necessarily relying upon a calculator. This way is possible. It gets us the same place, but you may have to break out the calculator, okay? So you decide. Both ways are perfectly acceptable. So what's going to get rid of a 1/5 power was a 5 over 1, the reciprocal. Well, 2 to the 5th is a nice one. I don't know many of the fifth powers off the top of my head, but I do know 2. 2 to the 5th is 32. So that's the way I would suggest doing a problem like 3 and 4, okay? Do we have any questions about what we've seen so far? Yes. Hmm? Okay, so let's talk about our powers one more time, okay? So let me find a little spot. I'll go up here at the top. So the rule is anything to a fractional exponent, the top stays a power, the bottom is our index and our radical. You can do the square root, cube root, fourth root first and then the power, or you can do the power first and then the root. Either or will work, but please know how to go back and forth between those things. Yes. So please make sure we're going back and forth between those things. Okay, so let me remind you one more time. The numerator acts like a power. The denominator becomes our index. If our denominator is a 2, you don't have to write it, but you can. It doesn't hurt a darn thing, okay? Hopefully that at least, helps you see how those go back and forth. So the most common ones, b to the 1/2 is just the square root of b. B to the 1/3 is the cubed root of b. B to the 3/2 is the square root of b cubed. Some of those are some of the most used ones, I would say, that we're going to see. So, just flipping back and forth between those notations is going to be important, okay? Does that at least clarify some of those things for? Okay, great. Okay. Let me show you one more time. Yeah. 3 for F. Oh, okay. So remember, if it's kind of that prime factorization thing. So if you see 8, I'm sorry. Do you remember there was a time back, probably in Algebra 1-ish maybe, where you took a number and you broke it down into its primes. Oh, 2 goes into it, and you kept breaking it down. Like that's 2 times 4, and that's 2 times 2 times 2. Oh, that's 2 to the 3rd. So if we want to know, a list of squares and cubes are very helpful to get into your brain. So for our list of perfect squares, if we start with 2, 2 squares, 4, 9, 16, 25, 36, those things like that. And then for cubes, it's kind of helpful to know, especially that 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. Those are the ones that you're going to see most often. But it's kind of that factor tree that we used back in the day. Did that help a little bit? Okay. Okay, so now we have left off at G. Could you please jump to G? These are just going over some of the rules we talked about in 4.0 mod. If the bases are alike and you are multiplying, keep the base, add the exponents. If you're dividing, subtract the exponents. So 7 minus 2 is 5. If you have a power to a power, multiply. So that's just reminding you of some of our simple rules for exponents, okay? Okay, so now let's jump, please, to number 4. See number 4 right here, okay? It says a farm in Canada has 218 alpacas on January 1st, 2016. After 8 years, the alpaca population has decreased to 187. Assume the number of alpaca decays exponentially. What is the 8-year decay factor? Well, we're going to really kind of say the function at 8 divided by the function at time 0. That would be that 8-year expanding. And so we're just going to take that 187 and we're going to divide by the initial amount, 218. And we should get a decimal value between 0 and 1 because they mentioned the word decay. And what that factor is 0.858. So for B, it says the number of alpacas on the farm was what percent of the start at 2016. We'll just change that into a percent. So it's 85.8%. Now, what is the 8-year percent change in the alpaca? Well, if you think about if we take 85.8 and minus off 100%, we're checking of how did it change from its original spot, which we always call 100%. We get that is a negative 14.2%. If your answer said, or if your problem said decay, expect that the percent change should always be negative. If it said, instead of decay, if it said growth, expect that your percent change will always be positive, okay? Now, part D says, assuming the alpaca population continues to be modeled by the same exponential growth, how many alpacas can be expected to be on the farm by January 1st, 2032? Okay, so let's think about, this was an 8-year change. It goes down by 14.2%. And we use that 85.8% every time to figure, every 8-year block, okay? So from 2016 was the start, up to 2032 is, let's do some math here, 2032 minus 2016 is a 16-year span. If we divide that by 8, that means we have 2 blocks of 8, okay? 2 times 8 is 16, however you want to think about it. So we have to do the math twice. So the alpacas, if you did scroll back up, started at 218. We have to multiply by that rate of change, or I'm sorry, that the percentage that gives us what the number is, that 0.858. But we have to do it twice, and that would be twice as an exponent. So if we do 218, and you can either put into your calculator, because there's only 2 of them, times 0.858 times 0.858, or you can do times 0.858 squared. Both will get you exactly the same thing. Now, these are creatures, so it's customary to round to the nearest whole number. That is 160 alpacas. So by 2032, we would expect that there is only approximately 160 alpacas left over, okay? So then E is kind of interesting. It says 8 years is quite a long time. What if we only wanted to know the 1-year decay rate? Well, if we know that 0.858 represents our rate for 8 years, the rate for 1 year, we would actually take the 8th root. Or you can even think, if you were putting it into a calculator, taking it to the 1/8 power. Now, if we do that, I'm going to go approximately every year we could use the 0.981 as our rate if we wanted to do it year by year by year by year. How could you check your work? Well, if you put 0.981 into a calculator, you put it to the 8th power, it should give you that 0.858, okay? So what's the 1 year percent change? Remember, we take whatever our rate is, take off 1, or 100%. So if we do 100%, so that's 98.1 minus 100. That's why we get a negative. We get a negative 1.9% change. Okay. So that, did I subtract right? 0.981 minus 1. No, I did not subtract. Well, I guess that would be percent-wise. Yeah, I think that'd be okay. Okay. And then we want a function that is a yearly, if it's just time in years, okay? So remember how these functions work. Our starting number comes first. So remember, our alpaca population started at 218. That's always your starting population. That comes first. Then we are going to put that yearly rate that we just found, that 0.981, to a power of t. Now, if we wanted to use the original, that 0.858, like if we never did the 0.858, and this t is in 1 year blocks instead of 8 year blocks, you just would take your t and divide it by 8. Those formulas are equivalent. I like this one a little better. This one, because you're inputting 1 year at a time, you have to divide by 8 for it to work. Okay, so that's a little bit about, you know, alpaca stuff and how we can find the exponential rates and changes and things. At this time, go ahead and turn that in. Please go into your iMath, click on the calendar for today. Please go to your iMath, click on the calendar for today. And if you click on the calendar for today, you should find this pre-class M44. We're going to work on that together. Now, the first portion here is just a little introduction. It is going to give you some information about solving some things with exponents. So if you want to take some time to look at those examples, they're helpful. Now, I don't know if your examples and my examples are the same, but we'll walk through mine and hopefully that will help you do yours. Okay, so the first one says to solve each of the following equations for x. If there are multiple solutions, write them by separated by a comma. That's really important, okay? So my first one is x squared equals 81. I don't know what yours is, but it's probably a squared at first. In order to solve that, let's solve it on paper to the side here. We have to take a square root, but that's the type that we must have a plus or minus symbol in front. And then the square root of 81 is 9. So for iMath, for my purposes, I am going to do 9 comma negative 9. Or you could put the negative first and then a positive. But that's how we would do ones like that. Make sure you separate your answer by commas, okay? Now, my next one is a cube. So that one will only have one answer. Mine isn't a perfect cubed, so I believe that you can just type 86 Well, if you use the little yellow arrow box, there is a cube root option. And then you can just type in 86 for me. So you can either use the box to do a cube root if you use that little yellow box. It also looks like you could type in the words root 3 and then the number. Okay, so you could actually type root 3, 86. So if it's a fourth root, you could do root 4 and so on. So that is our second spot there. Now let's talk about solving one like C for just a minute. See that 4 that's in front of the cube root or the cube on the X? You must get rid of that 4. Maybe yours is a 6, maybe yours is a 10, maybe yours is an 8. Just divide both sides by that number first. Now, hopefully they've made it nice. If not, you could just write that. For my purposes, 10.6 divided by 4, I get 2.65. Okay. So then once I have that value, then I can just go ahead and I can write, remember, you could write root 3 because X is the cubed root of 2.65. So I could, instead of using the yellow box, I could write that. So I'll give you guys a chance to solve your equation. Make sure if your power is a cube that you are doing a cube root. Okay. Now that we have that, the most complicated of our equations, but it's still not too horrible, is D. Let's do D together, okay? So it's 2x squared plus 6 equals 29.4. Now, I assume your numbers and my numbers are different, but it's still a similar procedure. So you might want a sheet of paper. So if you want to watch mine for a minute, then that will guide you for yours. You must subtract off the number or add the number first to isolate that variable, just like any other equation. Now, if there's a front coefficient, which mine is 2, yours might be 2 or 3 or whatever, we have to divide that off first. So I get that x squared equals a number. My number is 11.7. Your number might be something different. What do we have to put in front of the answer to if we inflict the square root? What do we have to put in front of that symbol? The plus or minus. Now, I don't know if they'll accept the plus or minus symbol. I'm going to try it here just to see if that's an option. So if you type plus then minus, and then root 2, and then whatever your number was. So I got 11.7. Let's see if they'll accept that. Now I'm going to separate them each by a comma. Oh, for square roots, they just like squirt, SQRT. And then put whatever's in your square root in parentheses. So I would put squirt 11.7 and then negative squirt 11.7. So that's the first ones there. I'll let everybody get themselves caught up. Do we have any questions about those? Yes. Okay. Now that we've done that, there is a little section here. It says, we know that exponential functions have constant 1-unit growth factors, but it's also true that their growth factor is a specific constant for each interval size you pick. So if it depends upon the interval that you pick. So here, like, what if you pick from 2 to 6? So it says, after reading the short paragraph above, what does it mean for an exponential function f, where y equals f of x? We could choose an interval size, a delta x, and there will be a constant value that we can multiply f of x by to get the new value when x changes that amount. I think that is a legit choice. So let's put a little x there. F has a constant 1-unit growth factor, but does not have a constant 2-unit growth factor. That's out. Whenever x changes by 2 units, the value of f of x is multiplied by the same constant value to get its new value. I think that that is a possibility. Let's see. Yeah, I think that's a possibility. If you change x by 1 unit, the value of f of x gets multiplied by the same constant growth factor as if it would be if you change x by 3 units. That's incorrect. Whenever x changes by 5 units, the value of f of x is multiplied by the same constant value to get its new value. I think that one's a yes too. Yeah, I think we're good there. Okay. Now we need to jump down below and we have an actual little scenario. In this case, mine's about bacteria. Your micrograms might be 4.2, 5.5, 6.2. Mine's 4.7. Okay. Now it says at time 0, there is a 4.7 micrograms of bacteria in the petri dish or whatever it is, okay? The researcher's study in the bacteria notes that the mass appears to quadruple, so it multiplies by 4 every 50 hours. So we've got a little chart here. Let's fill out the chart, okay? So if yours is 5.2, 5.5, you're going to multiply by 4. So here I'm going to do 4.7 times 4 because that's what mine is. If yours is, whatever yours is, multiply by 4. And you're going to keep multiplying by 4 each time. So, you know, mine's 18.8, and then I'm going to multiply by 4 again, and it's 75.2, and then I'm going to multiply by 4 again, and I finally get, or multiply by 4, yeah, I'm going to keep multiplying by 4, okay. So it says fill in the table for the missing values. I've done that, okay. The 4 value is the 50-hour growth factor. The 4 represents the 50-hour growth factor for me. Does yours quadruple? So, yeah, that's just your growth factor every 50 hours. And then it says, what is the 50-hour percent change? Now here, this is a little different, okay? Let's think about for a minute. If we start at 100%, we multiply by 4, and it becomes 400%. How much did that change? Well, 300%, you got to subtract. So that would be 300% for me. If yours says quadruple, you should have a 300% change as well. You want to make that positive because that bacteria is growing. Okay, so that, hopefully everybody's got that to work. And then we just have one last little piece here. It says, when sunlight hits water, not all of it penetrates the surface. As you travel deeper, a larger percentage of the light will be deflected, reflected, or absorbed. The exact percentage of light that reaches a certain depth depends on several factors. In one lake, a researcher discovered that any change of 10 meters in depth reduces the amount of light by 22.8%. What is a 10% change in the amount of light? Well, I don't know what your number says, but it might be that 22.8 like me. Think about the fact that they said that it's going down by 22.8%. So just make sure you make that negative. And then make sure you're picking percent. Okay. Now right underneath that it says, what is the 10-meter decay factor in the amount of light available underwater in this lake? Now, the decay factor, remember, is you start at 100, you take off 22.8 to see what's left. And that would be your decay factor. Remember, it's a number between 0 and 1 in decimal form. 100 minus 22.8 is 77.2%. But we want to write that decay factor as a decimal. So that would be 0.772. So I believe that that is now done, which is awesome. So now, if you could go back to your calendar for me, click on October 13th. There's a homework 4.4. Could you please, at this time, open up homework 4.4? Okay. Open up your homework 4.4. We're going to take just about 5 minutes to maybe get started with that. Okay. So let's take a look at this first question. I think will get us a good start at least. Okay, so let's look at the question. It says a sunflower is planted in a garden and the height of the sunflower increases by 7% per day. 2.78 days after being planted, the sunflower is now 9.7 inches tall. What is the 1-day growth factor? Well, let's think about the fact that if it is growing 7% per day, they've given us a growth factor information. If it started out at 100% and if it went up by 7%, what is now our new percentage? 107. You just need that decimal. So I believe what they want in this first spot, if I can get my mouse to go over to it. There we go. I believe that they just want that 1.07. Okay. Now, how tall is the sunflower? Let's just make sure. Okay. Then it says, how tall is the sunflower after 3.78 days? So you see how from 278 to 378 is exactly 1 day? You see that? From 278 to 378 is a 1-day growth factor. So if we just take 9.7 times the 1-day growth factor, let's try that. So I'm just going to put in here instead, I know that it was 9.7. 1 day later should be times 1.07. Yeah. And then this would be 2 days later. So it would be 9.7 times 1.07 to the second power because it's 2 days later. So the 2-day growth factor for me is 1.07 squared. And I am not going to do that and make iMath yell at me. So you'll notice that I just put it in. And thank you for reminding me how picky it can be. Okay, so let me go over that one more time. From 278 to 378 is a 1-day growth factor. So I can just use 1.07. I don't need necessarily the formula. If it's an exact jump of 1 day, it will always go up by 7%. So I think that's what they wanted us to do there. Okay. So if it's a 2-day growth factor, it went up to the second power. So if it's a 3-day growth factor, it's that 1-day growth factor to that new power. So that would be 1.07 squared. Okay. So if it's a 3-day growth, 1.07 cubed, 4-day growth, 1.07 to the fourth, and so on. And again, check your numbers. I don't know if your numbers and my numbers are quite the same. Okay, now we're going to jump to question number 2. Okay, it says an exponential function has a 1-unit growth rate of 1.37 and the starting value is 16. Start by sketching a graph of f, which I can put up on the board here in a second. What is the value of f of 4? So, when you know the starting value, our function is always the start times the growth factor to whatever thing you're plugging in. So in this case, we would plug in 16 times 1.37 to the fourth power. So that's what I'm going to type. I'm going to let iMath do that. So it's 16 times 1.37 to a power of 4 because my input is 4. Okay, so let's go over. That's the starting value, 16. The growth factor is 1.37. I am inputting 4, so 4 units later. So I think that should be okay for there. So the function is 16, your starting value, if your starting value is different than mine, or my growth rate, 1.37, to a power of x. So I just took out the 4 and put in an x. They did say a function of x. We know that. See, if they didn't use, if whatever variable is there should be the variable there. Okay. So that is what they want there. Now we're going to do it again. What is the value of g of 6 if our starting value is 2 and our growth factor is 1.24? So it's going to be our starting value of 2, our growth factor in parentheses, or whatever power we're taking it to, in this case 6, that is our power. Our exponential function, our input is our power. And now let's take out the 6 and replace that with an x. So mine's 2 times 1.24 to a power of x this time. We want a generalized formula. So remember, the front number is always your g of 0, f of 0, your starting value, or if they say your starting population, this is your growth factor to a power of x. So that's getting you started. You have 5 homework Sunday. So work on homework every night this week. Work on late work. Get yourself all caught up.